Okay, continuing the preceding clip. We had this picture. I believe we had the theta I prime indicated here. Theta I prime being the angle of incidence of the ray with the normal to the point, at the point of incidence. Okay, so I've written a few things in here, just clarify, or just collecting some of the symbols. Okay, so theta I prime is what? Well, theta I prime is going to equal theta I minus theta R, this angle, plus this angle here. Now what's this angle here? Well, this angle here is equal to this angle here, because this line is parallel to this line, so this hypotenuse of this triangle constitutes a transversal of two parallels. So we have this angle and this angle being equal. So that theta I prime is going to equal this angle, theta I minus theta R, plus this angle, which is equal to delta x minus A over R. Now, delta x minus A over R. First of all, let's come down here and simplify A slightly. Theta I is delta x over R. Theta R is delta x over NR. Multiply that by 2R, and you get an expression for A. And then A is 2 delta x minus 2 delta x over N. So this 2R times theta I minus theta R here becomes this. And that's of course your A. Now, when we subtract this from delta x, what do we get? We get delta x minus 2 delta x. Well, that's going to equal a negative delta x. So this term here, let me get the right color of chalk, this term here is going to be negative 2. I'm sorry, it's delta x minus 2 delta x. I'll write it out that way, delta x minus 2 delta x. And then we're going to have minus 2r times theta, or well, it's going to be minus the negative 2 delta x over n. And then, of course, all that's over r, so we're going to put an r here, an r here, and an r here. We have then delta x over r minus delta x over nr. That's probably blocking the board for a lot of that. But again, we're just substituting the 2 delta x minus 2 delta x over n for the 2r times theta I minus theta r. And writing out the terms that we get and then dividing each of those terms by r. So this simplifies to this. It's rather straightforward. Well, we have a delta x over r and a delta x over r. Then we have a minus 2 delta x over r. So the delta x over r terms all go away. We have delta x over nr, and let me correct a sign here. This should be positive. We have minus 2r times minus theta sub r. So it's going to be minus the minus 2 delta x over n. So we have a negative delta x over nr and a plus 2 delta x over nr, and we end up then with a very simple expression, delta x over nr, and there is our angle of incidence of the ray as it's incident on the back of the cylinder. Okay, now that we have an expression for theta sub I prime, we're in position to figure out theta sub r prime, since we know that the index of refraction here is n, here it's 1. We'll do that in just a minute, but just before we do, a little detail that's going to help us in a minute. This delta x minus a that we evaluated here is just this minus this plus this. In other words, you see where these three expressions came from this fraction, or this fractional expression. And we see that that's just going to be equal to delta x minus 2 delta x being negative delta x plus 2 delta x over n. And then we just factor out the delta x, and we get delta x times 2 over n minus 1. Okay, so that's the expression for delta x minus a. That's going to be important in a minute when we try to figure out where this thing focuses. We got to know, once we find the angle here, we've got to know how far we are from the axis, so we see how far we've got to go to get there. So that should be fairly clear. Okay, so up here we have theta r prime over theta I prime is going to equal n over 1. You can check out Snell's law. The refracted now goes into the region with index of refraction 1. The incoming ray is in the material with index of refraction n, and we simply solve that for theta r prime, which is just going to be n times theta I prime. Now, I didn't write an intermediate step. Here's theta I prime. When we multiply it by n, we just get delta x over r. So that's kind of neat the way that works out. Now, that doesn't mean that this ray is parallel to anything over here, but we end up with our final angle of refraction equal to our initial angle of incidence, and that's kind of interesting. Okay, and you might look a little more closely at everything and see how that works out. But now we're in the position where we can easily find this distance, because we know this angle to be delta x over r, and we know this distance here to be delta x times 2 over n minus 1. So we have this triangle. I think I'll go ahead and use green here. We have this triangle where this side is delta x times 2 over n minus 1, and this angle is probably a bad idea to try to write that in. That just says delta x over r. Okay, so this angle is delta x over r. So the sine of that angle is delta x over r, and we're trying to find this distance, and the tangent of the angle would also be delta x over r. So that to find this distance, the tangent is this side over this side, so delta x over r is equal to this side over this side. So this side is what? Okay, well, I'm going to leave that for the viewer to solve.